and welcome to my YouTube channel, where every episode I take a physics topic and really try to explain it in a simple and understandable way. Now some episodes are just going to be fun physics facts, but most I'm going to try and tie in to the current school curriculum. So when that's the case, I'm going to put the key stage in the episode title. Right, so this one's a fun physics fact episode and it's been requested by a lovely viewer. I've been asked, what is antimatter? It's a term in particle physics used to describe a material composed of antiparticles. Sounds like something out of a Marvel film. I mean, it's basically the opposite of normal matter. But before I go into antiparticles, let me briefly explain what particles are. Yep, that makes sense. The word particle can be used to describe various types of really small objects, like protons, or dust, or gas particles. But particle physics focuses on the smallest detectable subatomic particles. This is so Ant-Man. To the quantum realm. At the highest level, these include protons and neutrons, which are composite, so they're made up of other stuff. They both sit in the category of baryons. So both protons and neutrons are a type of baryon. But if we break these down even further, as if that's even possible, then we know they are made up of even smaller particles called quarks. Quark? At the same level as quarks, we have another type of subatomic particle called a lepton. And electrons sit down here in this category, so an electron is a lepton. There are 6 elementary quarks, which are up, down, charm, strange, top and bottom. So a proton is made up of 2 up quarks and 1 down quark. And a neutron is made up of 1 up quark and 2 down quarks. How cool is all of this? This is particle physics, guys! Okay, and there are 6 types of elementary leptons too. These are the electron neutrino, the muon neutrino, the tau, and the tau neutrino. You heard the name neutrino a lot there. So a neutrino is very similar to an electron, but it has no electrical charge and a really small mass. They're actually one of the most abundant particles in the universe, but they don't interact much with matter, so they're really difficult to detect.
Hello?
Anyways, so now we know the 6 types of quarks and the 6 leptons. Now these 12 particles all sit under the category fermions. Oh my gosh, we're learning so many new names today. It's
a whole new world.
So as well as there being fermions, which remember refers to both quarks and leptons, there's also the boson particles. These include particles like the photon, the Higgs boson, now that one's pretty popular, gluons, there are other particles, but I'm not focusing on these today. Right, so in our standard model, we have fermions, which is the umbrella under which quarks and leptons sit. We have bosons, and lastly, but by no means least, we have antifermions. Yes! On to the good stuff. Antifermions are the antiparticles of the quarks and leptons. So where I explained there are 6 quarks, up, down, charm, strange, top and bottom, their paired antiparticle and 10 points for originality in the name are anti-up, anti-down, anti-charm, anti-strange, anti-top and anti-bottom. Likewise, the 6 leptons of electron neutrino, muon neutrino, tau and tau neutrino also have antiparticle pairs. These are the positron, the electron antineutrino, the antimuon, the muon antineutrino, the anti-tau and the tau antineutrino. With all these antifermions, they have the exact same mass and spin as their counterparts, but they have the opposite charge. So an up quark has a charge of 2/3, but an anti-up has a charge of -2/3. and an electron has a charge of -1, but a positron has a charge of 1. And this cascades up to baryon level, so a proton, which is made up of quarks, can have an antiproton as well. And also at matter levels, so you could produce an antihydrogen from a positron and an antiproton. But I know what you're thinking. If a neutrino has 0 charge, then what's an antineutrino? At the moment, we don't really know. They're seen as sort of the same thing, but they're produced alongside different particles. So you can only tell the difference depending on whether they're produced alongside particles or antiparticles. Alright, so that's the basic, like proper basic, understanding of the Standard Model. So if you want to know more, please give it a research. There are 61 known elementary particles in the Standard Model, so I've really only scratched the surface with this. Alright, now the big question. What would happen if matter and antimatter were to collide? Currently, teeny tiny amounts of antiparticles are produced daily at particle accelerators and stuff. But we've never been able to create enough antimatter to experiment because it's so expensive and really tough to handle. However, theoretically, if a particle and its antiparticle were to collide, so like an electron and a positron were to collide, it would lead to their mutual annihilation. So they would explode and produce matter, antimatter, and energy in the process. Boom! But don't worry, it seems like the universe is composed mostly of normal matter rather than a perfect mixture between the two. And this is actually a conundrum and one of the biggest unsolved mysteries in physics. Like, why aren't there equal amounts of matter and antimatter in the universe? Well, thank goodness, in my opinion. Don't want particles annihilating themselves left, right and centre. Also, can everyone just be really careful at these particle accelerators? They're going out of their way to produce antimatter. Like, that's scary stuff. Wow, that was a seriously fun episode. Well, for me it was anyways. Thank you so much for listening. I hope you enjoyed it. If you did and you want to learn about other cool physics facts, then please like and subscribe and watch all of my other videos. And if you want to learn about a specific topic, please leave a comment below and I'll try to do a video for you.